Hello, everyone. Hopefully you can see my screen. So my talk today is entitled "What Java Developers Need to Know About Observability." So my name is Ben Evans. I'm a senior principal software engineer at Red Hat, and my role there really is observability as part of this idea about the long-term health of the Java platform. You see, as we were just talking about just before the session started, Java's been around for 25, 26 years. And it's doing pretty well for a middle-aged language. But I want to make sure that we get the absolute most we can out of this wonderful platform. I don't want to see it fall by the wayside. I don't want to see it not keep up with the times, especially as we move into the age of cloud. So that's really what I do at Red Hat, is I try to think about the future of the platform. Okay, my email address is on the slide if you have any questions or you want to talk to me after the session. So about me. So before Red Hat, I've done a bunch of things. I was lead instrumentation at New Relic, which is where, and before that, I co-founded a company called JClarity with Martin Verberg, which we sold to Microsoft. So I've had this sort of interest in performance analysis and observability and things like that for many, many years now. Going back all the way to one of my first jobs, which was at Morgan Stanley, where I actually performance tested the systems that we built to conduct Google's IPO. That one is a fascinating story. Don't have time to tell it now, but hopefully next year, if we're meeting in person, you can buy me a beer and ask me about it then. Along with my sort of career in finance and performance analysis, I've also been heavily involved in the community. I'm a Java champion and have won various awards, including the Java 1 Rockstar Speaker Award. I've been very involved in the standards body, the Java community process, and I live in Barcelona now, which is lovely. But before that, I spent 20 years living in London, where I spent a big chunk of time working with the London Java community, which is one of the largest and most successful Java communities in the world. And during my time working with them, I helped found a project which you might have heard of called Adopt Open JDK. So that's me. It's probably enough about me. So let's move on and actually talk about what I'm gonna talk about for the rest of the next, I guess, 45 minutes or so. So here's what we're going to talk about. We're going to talk about the current state of Java. We're going to talk about cloud native. We're going to talk about OpenTelemetry and some other observability tech. But I wanted to do things a little bit differently today. So I thought I'd actually start with my conclusions. The reason for this is, well, firstly, it just helps to mix things up a bit and to just do things a little bit differently, because why not? But secondly, also, this talk is going to be quite architectural. I'm going to be talking about not the details of how you implement observability, or there's going to be not much code at all in most of the slides until the very end. But instead, we're going to think about the architecture and that kind of higher up level of what we want to do with observability. So in case that's not your cup of tea, I think I won't keep you hanging on, and I'll start by presenting my conclusions first of all. So if you don't want to have an architectural talk, if you want to go and make yourself a cup of coffee or anything like that, you can just take this slide, and this is the takeaways from the talk. So upgrade to Java 11. If you're still on Java 8 and you're running in containers, you are missing a trick. Java 11 is much better in containers, and 17 is going to be better again. I'm kind of a cautious person when it comes to my technology choices, so I would not recommend moving to Java 17 until at least early 2022. The 17.0 release has just come out, but there haven't been any time for any patches or any updates to it yet. So there may well be bugs which get fixed in the first update. So I think I'll probably start deploying my first actual servers and start recommending people upgrade properly from early next year. I'm already working with 17, but as we'll see a bit later on. But I think that widespread migrations can probably need to wait a bit. Once you've done that, once you're running 11, you then need to size your container correctly. Moving to 11 is going to change the way that your Java application uses memory. Typically, you may well see heap size savings of 30 or 40%. So you will need to size your containers or recheck the size of them if you've upgraded from 8 to 11. And make sure you do size those properly, both in terms of memory and in terms of CPU. In particular, don't use single core containers to house Java applications. If you do that, what will happen is you will get a serial GC, not G1. And you very definitely want G1 when you're running in containers. So therefore, you must make sure that your container size has at least 2 CPUs in it. Also, because of the way that the heuristics and the JVM's runtime determination of GC flags works, it's a very good idea to explicitly choose the memory size. So set XMX and any other GC flags you want. Don't trust the defaults. Set those flags directly, because otherwise, when you're running in a small container, the heuristics may not do what you think they do. And I've seen. Well, I'll show you some slides which justify that in a sec. Okay, so once you've done that, once you've got your container baseline correctly set up, the next thing to do is to choose an observability tech stack. So this probably will be OpenTelemetry, Micrometer, which came from the Spring project, and Prometheus. That's, I would say, probably the core of what you want to build your observability tech out of. And then finally, enable JDK Flight Recorder, JFR. Okay, so those are the conclusions. If you don't want to hear about architecture, then that's your takeaways from today. Okay, everybody that's still here, let's see what the current state of Java is. People always love these slides. So this one actually is quite old. This one actually dates back to about February, and it actually shows you that Java 8 was 35% of the market. But I've got some trend information as well, which is a bit more up to date. This goes up to April. So this shows you that Java 11 has crossed the 40% line and is very definitely trending towards parity with Java 8. Where these numbers come from, by the way, before working at Red Hat, I worked at New Relic, and New Relic monitor tens of millions of production JVMs. And all the customers who opt in to sharing their data with us, to allow us to see in aggregate what's going on in the market, which is virtually all of them. Only a few customers didn't do that in New Relic. Most people actually are perfectly happy for us to see aggregated data about what they're running. So these numbers are not a self-reported survey. These numbers are actual data from running instances, and tens of millions of them. Gartner, I think, estimate that the New Relic data set comprises roughly 1% of all JVMs running on the planet today, which is amazing. That's a very, very big sample size. So of course there are biases in this data, but I'm convinced that this is one of the best available data sets that we have for making these sort of large scale pictures of what's present in the Java market as a whole. Okay, so that's where the numbers come from. Okay, let's talk about containers. This is huge, 62%, nearly 63%. And again, this is a February number. This number was going up very, very quickly, right up until the point where I left New Relic. But containerization is a fact, and the numbers are, are pretty clear. 63% of all JVMs are containerized. That's just a huge number, and has shot up in just over 12 months or so. Well, one of the things that I said right at the start was you also need to be careful about single core containers. Now, why did I say that? Well, it's because of this slide. Yeah, look at that number. Single core containers are 59, 60% of the containers that we see. So that means that 35% of all Java runtimes are running on a single core container and are probably picking up bad defaults. So when you finish watching this talk, go and check what your Docker containers are actually running in. Check to see if it's single core. Check to see what that means about the assumptions that you're making about the system. So, for example, that means 35% of all of your runtimes are doing fully stop the world garbage collections when they don't need to be. In a dual core container, those stop the worlds will completely go away because it will be able to run G1 on 2 CPUs. Also scary, people not setting XMX in their container. That is likely to cause you, especially on Java 8, an out of memory error. And again, over a quarter of all containers do not have XMX set. You need to set that number. So there we go. That's a quick roundup, hopefully data-driven, which justifies some of my conclusions about what you should be running for your containers. That's not observability. But it just goes to show that if you don't set these things up, if you don't actually understand how your applications are running, there can be all of these problems, all of this low-hanging fruit that's just hiding in your application setup that you don't know about. Okay, so our reasons for using 11 in containers are that it's container aware. 8 is only mostly container aware, and it's not going to get any better. All the things which were going to be backported have been backported now to 8. So 8 is not going to get any better at running in containers over time. It's also now 2 major versions behind. So, there really is no real reason to be using 8 anymore, I would say. The version of G1 is different in 11 than it is in 8, and it's a hell of a lot better in 11. Compact strings provide a major source of heat reduction, so your applications will use less memory. They will just run in less footprint, and that's got to be a good thing. And of course, Java 11 has JDK Flight Recorder, and of course, Java 17 brings JFR streaming as well. So those are our primary reasons. So now let's move on, talk about cloud native. What the previous slides should have convinced you, I hope they convinced you of this, is that cloud native is already our reality. We talk about moving to the cloud and so on and so forth, but the truth of the matter is it's kind of already here. 62% of our apps are containerized, and that number is rising fast. Not only that, but as we start to move into the cloud, a couple of things happen. First of all, we end up with a lot more microservice architectures, and that increasing complexity means that there are more tiers, there is less of a structure than you might have seen. More services are talking to each other more frequently, and managing that complexity is a challenge. The response to that challenge is observability. Observability is a new area. It's almost like a new discipline, if you like. It's grown out of the APM segment, for application performance monitoring, or application performance metrics, monitoring. The idea of having either a system that you've built yourself to monitor your systems, or to buy a vendor product in order to do so, or to deploy an open source solution. But it is different. As we'll see, the older approaches that we used to use are not really all that suitable for observability. And you might ask the question: is that really true? Is observability, is it just APM with some new marketing terms? And I would say that really no, it's not. And the reason why I would say that it's not is really that there are 3 separate pieces to it. First of all, excuse me, the number of application components in a typical microservice architecture is just much higher. There's just more complexity. There's more stuff in our application architectures now. And I refer to this as it's sort of a reprise of an earlier theme that we've seen, which is the idea of livestock versus pets. Now, if you haven't heard this term before, if you're old like me, you remember back in the day before you had DevOps and before you had site reliability and all of those functions, you had systems administrators. And what systems administrators used to do was to administrate systems, as the name suggests. And they would hand build systems. The idea of a server in those days was a physical piece of hardware. So you'd have hardware, you'd install an operating system on it, you'd install packages from the operating system, and they would be upgraded. So the image itself was mutable. The concept of a server was something which was looked after by an individual human, handcrafted, perhaps with a little bit of automation, but there would be an upgrade. The state of the server would change over time as the operating system and packages were updated. So it was like a pet. It was like something you hand reared. In the world of cloud native, in the world of containerization, that is gone. We don't have that. What we have now, effectively, a livestock. If one of your animals is sick, you shoot it in the head and get another one. Spin up another container. You don't bother upgrading things if things change. The instances are immutable. Once they're created, just like as we are with immutable objects, it is created in the only state it will ever exist in. It will never be upgraded. It will never have additional packages installed. It's created in one state and it dies in that state. And if something's gone wrong, you don't necessarily spend a lot of time figuring out how to upgrade it to make it better. Now, as a result, the debuggability of containers is much harder. because it does come from this philosophy of, well, the instance is immutable and so forth. So that complexity and that livestock versus pets tension has been a major question about how we do observability. How do we understand what our systems are doing in this world? The next problem that we have is data volumes. The telemetry data volumes for a microservice and cloud native system are just much higher. Partly it's because there are more components, and partly it's because we are now have the capability of collecting more data. And related to that data volume, that challenge that it presents, the response is that there are actually different ways to do observability architecture. And this is probably the most critical point I want you to understand in the whole talk, is that the way that we do observability matters. The way that we confront the challenge of there being just too much telemetry data and how we respond to that data volume affects not only the architecture of the observability systems that we deploy, but also our architectures of our applications themselves. We also might see that there are lots and lots of smaller services. There are now multiple relevant personas. So a developer persona, a DevOps, an SRE. These types of roles are also playing a part within the architecture of cloud native. Tech stacks are becoming increasingly heterogeneous. You know, the old days of, well, you had a web server tier and then a Java application server and then a database. It's not really the same anymore. You know, we might expect components written in multiple different languages, which all need to speak similar protocols for observability. And then, of course, the service clusters are much more dynamic and they have much higher scale out than we've previously seen. Okay, so let's cut to the architectural approaches. So as a response to all of this, there are really 4 things you can do if you want to get a handle on your observability. The first thing to point out before we discuss each of these in turn is just how much data there is. I sometimes describe this as being a bit like quantum mechanics, you know, because in quantum mechanics, when you observe something, you cause a change. You know, you have the idea that you know, in Heisenberg uncertainty, if you know exactly where something is, you can't observe its momentum very well. That there is an essential fuzziness in the nature of reality at small scales. Now, in our case, it's really all about resource usage. Observing a value, observing a system, costs resources. It costs CPU to perform the measurement. It costs bandwidth or disk space to write that data somewhere. Typically, it's network bandwidth. So how does that work? How does that affect the system's performance? If you do too much observing, aren't you compromising throughput for the application as a whole? So that question, that delicate balance of how much can you observe, how much overhead are you prepared to tolerate for your observability solution is actually a key one as well. Now, from that, there are really 4 different approaches that people have come up with. The first of them is to perform data aggregation on the host itself. And what gets sent into the observability system, which in this case is a SaaS system, so probably a vendor product, I would say, is an aggregate. So you never send the raw points. You only ever send some sort of aggregation. And that aggregation could be a sum over a period. It could just be last update. It could be some sort of sampling. There are different aggregations that we'll talk about later on, which could be the case. The second piece is to actually send all of the data points. But if that's to a vendor product, then you have the challenge that needs to be within a single cloud region. You do not want to be in the business of paying the egress bandwidth to cross AWS regions or Azure regions in order to send all of the data points. If you genuinely want everything, you have to restrict how far that data is actually sent. And that is reflected in the third architecture as well. The third architecture says, don't even send it to a SaaS. Keep everything on your Kubernetes cluster. And basically at that point, you can now tolerate much higher data volumes. So there's a couple of different solutions which use this technology called eBPF. If you don't know what eBPF means, basically it's what happens if you start from thinking about the kernel having firewall rules. And the firewall rules are a dynamic set of rules which perform certain actions and routing and other logic within the kernel. And eBPF basically raises the question, what if this language was Turing complete and it can also be things other than networking rules? So effectively, it's a scripting technology which compiles to bytecode, not Java bytecode, but a different sort of bytecode, and runs in kernel space. So you can intercept and trigger actions on basically every kernel operation. So every file write, every network access, and so on and so forth. But you can do it entirely within the kernel without affecting anything at the application layer. Very powerful technology, generates an awful lot of data. There are a couple of open source projects under the CNCF, the Cloud Native Computing Foundation, who are starting to look at this. There's a project from Splunk, which I've momentarily forgotten the name of, and a project from New Relic called Pixie. They're open source projects, and they enable you to do observability at a very, very low level, but only within a Kubernetes cluster. And then fourth and finally is the roll your own. This basically is where you don't want to involve a vendor, and instead you feel like you want to build and maintain your own observability systems. This, of course, has as all of these do, they have their trade-offs. But the roll your own, I think, is a particularly interesting trade-off to have a look at. So let's take a look at that architecture here. So you have some sort of data source in your application. Maybe it's agent, maybe it's a collector of some sort. And then you feed that into, well, in this case, I'm assuming that you're using OpenTelemetry. A lot of my talk, the rest of my talk will be about OpenTelemetry. So it's pretty reasonable assumption, I think. So the OpenTelemetry collector takes the data which you feed it, which has come out of the application, whether directly but via manual sends of metrics or whether out of an automatic instrumentation piece. You feed that into some sort of ingest pipeline. As you might guess from the little graphic here, what some of the ones that I've seen actually use things like Apache Kafka for this. From the ingest pipeline, you have a data store. Then you have services to actually represent and visualize and do the work of presenting the observability data and the visualization. And then you have an observability visualization backend. So this could be something like, for example, Jaeger. There are lots of open source components for all of these. And I think I'm probably not giving away too many secrets to say that actually this description of the architecture is also how the vendors do it. So New Relic's architecture looks pretty much exactly like this. And I am prepared to bet at least a pint that most of the other vendors have got something similar as well. The difference, of course, when a vendor does it versus when you do it for your own systems is, well, vendors have to deal with multi-tenant. They have to deal with incredibly high volumes. They have to deal with data privacy and data retention records and GDPR and all sorts of other federal compliance, FedRAMP, for example, in the United States. So, and of course, if you're doing this for yourself, you kind of don't need to do that. Now, you still may have a problem if you're growing rapidly that you'll have to scale this pipeline yourself. But everything, hey, I did say this was an architecture talk. Everything is about trade-offs. And the decision as to whether you're genuinely going to roll your own or whether you're actually going to just make this somebody else's problem and pay for it is part of the trade-off that you will need to make when you undergo your own observability journey. Having seen the insides of a vendor, I mostly would want a vendor to do this, unless it was really a core part of my core competence for my startup or my business. I think I would want to outsource this. But there are other perfectly valid reasons why you might decide that you actually did want to stand up a pipeline like this for just your own applications. Okay, I can't actually see the chat window, so I'm just momentarily going to pause there and just check I haven't got any questions. So no questions. Okay, then we shall carry on. If I actually click this right screen sharing button, there we go. So what I'll talk about next is, we've talked about how observability fits in general. And I think I'm going to focus for the rest of the time today on OpenTelemetry. Now, let me explain what OpenTelemetry is. It's a set of open standards. It's free and open source software. It's maintained in a vendor-neutral foundation, the CNCF, and it has standards, formats, and libraries. Now, where did it come from? Well, if we go back in time a little bit, I don't know, 7, 8 years, the APM and monitoring sector was still maturing, but it was dominated by proprietary technology and proprietary vendors. And open source developers being what they are, lots of people decided that they didn't like that, and so they started up some projects in response. A couple of the larger companies also produced their own monitoring solutions and then effectively open sourced them. So one of the previous projects was called Open Census, which came from Google. Google's internal census metrics were then turned into open source and released as Open Census. So there were various different attempts to try to do some sort of open, standardized monitoring and observability solution. At the same time, as software becomes more complex and larger, the proprietary vendors started to realize that actually they had a bit of a problem, because as software gets more complex and larger, they had to match pace with the popular languages. So popular languages, popular frameworks all needed integrations, all needed work to support. So it's kind of like an arms race between all the different companies. So each proprietary company is kind of trying to keep pace with all of the innovations happening in the software space. At some point, there's actually an inflection point where, rather than maintaining closed proprietary stacks which try to cover the entire software space, it actually makes more sense to cooperate on an open source core and have the value provided by their products migrate up the stack, to migrate up into the hassle, not having the hassle of having to run an observability system yourself, into decent visualizations, into having dedicated product teams working on that. So what that means is that the companies that switch to open source led approaches gain advantage over those competitors who are still working with proprietary code. So that's basically where we are now. We are partway through that inflection where all of the vendors are switching over to use open source technologies. And specifically, a lot of the action is coming in OpenTelemetry. The two key projects which started and sort of merged to become OpenTelemetry were Open Tracing, which, as the name suggests, is a tracing product, and Open Census, which is metrics. So this is where we are. We have some standards which are emerging. And OpenTelemetry is really just those standards, those client libraries, and those wire formats. It's explicitly cross-platform. It's not purely a Java thing. There are folks from Node and Go and Python and .NET and Ruby and all the other languages are all here as well, and their data formats, are all very similar. The standard and the wire format is implemented independently of which technology platform we're talking about. It's also important to note that it is not a data ingest or observability backend. OpenTelemetry does not provide you with those stages of the pipeline and the data store and all those other things that I showed on the previous slide. So on this slide, it provides the collector, which is a terminator, an endpoint, and that's it. So the entirety of OpenTelemetry is essentially from the purple app box down to the funnel, which is marked OpenTelemetry collector. That's all you get. So if you want to roll your own, you're still going to have to provide all of the architectural components that I presented on the previous slide. It's also important to note that OpenTelemetry is agnostic to which architectural choice you make. So if you make the roll your own choice, if you make the aggregation choice, your role will send everything choice, OpenTelemetry doesn't care. Its architecture is designed to allow you to still make that choice completely freely. And the key way that it does that is via aggregation, which we will talk about a little bit later. Okay, so we have this emerging set of open source standards. Fantastic. Let's have a look and see what it looks like. What's the current status? What pieces do we have already? Well, it kind of looks a bit like this. I found this diagram on the OpenTelemetry site, and it's, I don't know, at first when I saw it, I thought it was a bit scrappy, but the more I look at it, the more I think there's actually quite a lot of interesting and useful detail on it. So it actually does show the components here pretty well. So, the pieces that we're building in OpenTelemetry are the core SDK, which is responsible for network transport, and the ability to create metrics and other instruments that we're going to want. We have the API, which covers traces and spans, as well as metrics, and at some point will also contain logging as well. I should mention here about the support down in the bottom left-hand corner. Long-term support. To be completely clear, this is not commercial support. This is merely a promise by the companies who are involved in OpenTelemetry that they will continue to be involved and continue to contribute resources to the support and maintenance of the releases for the defined period. So 3 years for the API and 1 year for the other components. I don't doubt that various vendors and various third parties will also sell long-term support contracts as well for people that want to buy them. Okay, so what's next? Well, I did say that these standards were still emerging. So let's take a quick look at the maturity. There are 3 parts, 3 pillars, if you like, of OpenTelemetry, of observability more generally, and they're usually called metrics, logs, and traces. Now, of those, OpenTelemetry has got distributed tracing to 1.0. So it's ready to go, it's production ready, and you can now track the progress of a single request all the way through your architecture across multiple services. You can use things like the standard, what's called the W3C trace context, to actually detect a single request as it passes through your application. The metric standard is pretty close. It is approaching 1.0 status. The protocol, by which I mean the wire protocol and the way the data is represented at the network layer, is complete and is stabilized. The API is in feature freeze, and I think it's pretty decent chance that we will reach 1.0 by the end of this year, and this will then provide us metrics both for the application and for the runtime. And it's here that we start to see a few differences between the various languages. You see, some languages like Go or Rust don't really have a runtime. I mean, Go has a garbage collector, but it's not really a full runtime. So there are differences in the way that we can represent metrics, and indeed what metrics are even available between various of the different languages and programming environments. So you just have to embrace that. You can standardize on the things which it makes sense to standardize upon, and for those things which are unique to the environment, you just have to treat them specially. It's less of a good story, I'm afraid, for logging. Logging is still very much in draft status. It's not expected to reach 1.0 until at some point in 2022. I would suggest that it's probably going to be something like summer 2022 before we see a completely stabilized and 1.0 logging as well. And logging should also be made clear. Logging in OpenTelemetry is a very general concept. If you're not a trace or a metric, you're a log, and that's how they think about them. I sort of feel that possibly is a little overgeneral. I would like there to be other forms of structured data, which are not just simply bags of keys and values, which is effectively what a log item is in OpenTelemetry. But the jury's still out on that. I think there's plenty of time to have that conversation and to see where we end up before logging is finalized. Finally, it's also important to note that there are both specifications and standards, as well as different specific language implementations. So the Java and JVM implementation is one of the most mature ones available. Other languages may have implementations that are less mature. So the standardization is one piece, the implementations is something else. So how do we get started? How do we start thinking about applying OpenTelemetry to our applications? Well, the first thing to remember is that in Java, there are always 2 ways to do instrumentation, which is manual versus automatic. Manual is you actually write into your code where you want to take a metric measurement. Okay, full control, but of course that provides you with direct coupling. You have to depend directly upon the observability libraries. If you're going to actually explicitly refer to a metric or a metric creation in your code, you will need to have those types visible in your class path. So you have a direct dependency upon it. And manual instrumentation is prone to human error. You may think that you understand exactly what the the parts of your application are and what the important ones are. But experience has shown us that in practice, humans are pretty bad at this. And you may end up with blind spots that you don't know are there because you haven't instrumented absolutely everything, which turns out to be important. So for that reason, lots of people also like automatic. Now, this is provided either by a Java agent or by a Java framework supporting the OpenTelemetry piece. This is not a Quarkus talk, but I just want to plug Quarkus and say Quarkus has full support for OpenTelemetry out of the box. All you need to do is to set a flag and import one library into your Maven POM, and it's there. It just switches itself on automatically, so which is kind of nice. If your framework doesn't directly support OpenTelemetry, you can use a Java agent. There is a Java auto instrumentation agent being developed as part of the Java working group in OpenTelemetry, and it's quite nice. It does automatic detection of traces. There's also some stuff there for metrics as well, we hope. It still requires config because you have to know not to instrument everything. You probably don't want to instrument down into Java lang invoke, for example. That's probably going to be the wrong thing to do. Problems with this: possible startup time impact. This depends precisely on how well you write your agent or framework support, but it can be an issue. Just depending on how much, in the agent case, how much bytecode you actually have to weave in order to get this thing done. There's also possible performance penalties for using it and making sure that you actually don't instrument everything and don't instrument too much so that it impacts your runtime performance as well. Everything requires trade-offs. Okay, so let's talk about traces. The big question about traces is sampling. Traces have to be sampled. This is a trade-off due to load. It's almost impossible to survive with an application which sends every trace or details of every trace to an endpoint. It can be done, but that's one of the within cloud region solutions that I talked about. Some of the vendor products actually do provide unsampled, every trace has data collected from it. But it is a trade-off, and it's not necessarily the right solution for everybody. So then that leads us to the question of, well, what are we sampling? Should we sample everything at the same rate? For example, should we sample more heavily traces which resulted in errors? If something resulted in a 400 or a 500 error code, shouldn't we be looking at all of those? And then there's also questions about exactly how statistically to conduct the sampling. So those are probably questions which are more at the architect level rather than the individual developer, but there's certainly something to be aware of. Just to remember that if you can't take all the data, how do you make sure you're not missing the important stuff? Metrics still being developed, but they're controlled by the OpenTelemetry SDK. When you make a metric event, you capture only the value, but also the timestamp and any metadata. And currently, OpenTelemetry defines 3 primary metrics: a counter, and a counter only increases over time. So a counter could be an example of, I don't know, let's say the number of major garbage collections you've had. Yeah, that number's only ever going to go up. A measure, which is a value aggregated over time. I might think here about, well, allocation. How much memory have I allocated over time? You could do that with a measure, but actually, so you could do that with a counter, but actually I might want to think, well, I might want it over some period. So a measure might be more appropriate there. And then an observer, and the way that this works is that the OpenTelemetry library, you define certain things as observers, and the OpenTelemetry library comes in and grabs those values whenever it wants to. That's one of the things, in the next point, that the aggregation is being performed by the SDK, not the app code. Very much, this is a case that the SDK is trying to make decisions based on what the correct way to aggregate is. So there aren't really good ways in OpenTelemetry to plug in your own aggregations, but pretty much all of the most common ones that you're going to want, especially ones that can be visualized easily from a backend, are included in the SDK. Very quickly, OpenTelemetry data is delivered over OTLP, which typically is protobuf over HTTP2 or gRPC. This is possible to do other encodings, for example, HTTP and JSON. I would advise very much against that. The default implementation, which is netty, it's HTTP2, it's protobuf, it's gRPC, all of that has been designed with performance in mind. And the people who've been building these are very, very performance conscious. So I would very much suggest use OTLP for message delivery, for observability data delivery, and make sure that you don't use anything other than the defaults if you possibly can. Okay, what are the challenges? There's a diversity of tools and technologies in use, which means that there's a large matrix of possible deployments. Someone in your organization, when you're adopting observability, has got to decide what observability architecture to use and to guide people into doing it. What you don't want to have happening is lots of different groups doing mix and match and laying out different architectures for their observability solution. And finally, of course, it is still maturing. There's a question around how do we get support for standards that aren't finished yet? To what extent do you really want to be deploying things that aren't finished? Sure, tracing's at 1.0. Metrics is kind of there, but it might still have a bit of delta. Logging's quite a long way off. So there's going to be a long tail for those older tech pieces that are already deployed. And then just to shout out, the OSS groups and standards need more participation. If you're interested in this stuff, come and join the Java OpenTelemetry group. We'd love to have more people involved. And logs are particularly difficult. Other things which you might want, Micrometer. Micrometer is a great tool for application level metrics. If you want to use Prometheus or we are using Prometheus, you can also think about doing things like collecting metrics from JMX and bridging that out to Prometheus. Some people use the microprofile metrics. I would tend to suggest that these are less suitable than Micrometer these days. I would think some combination of Micrometer and OpenTelemetry is probably going to be a better solution for almost everybody than microprofile metrics. In terms of the vendor solutions, I've just listed out the vendors there. They're all fine products. So pick whichever one you like and seems to fit your use case most. Okay, a couple of minutes, my final section. JDK Flight Recorder, JFR. This is a fantastic low-level tool for diagnostics and profiling data. It was proprietary in Java 8, it was open sourced in Java 11, and it has been backported to OpenJDK 8 update 262 and above. So if you're on a modern OpenJDK, so I think it's about 2 years ago now that it was first backported to Java 8. So if you're running a modern OpenJDK 8, you will also have the capability of Flight Recorder. It's low overhead. Oracle say about 1% to steady state performance. I think if you want to get useful data out of it, you're talking about a 3% overhead, which is perfectly fine for most people, in my opinion. How does it work? We use a ring buffer, and basically this sets up an in-memory buffer of past events. And then if you can SSH into the machine, you can dump the file, and that gives you something to load into it, which is okay. But you end up with a file which you for a single machine, which you load into a GUI tool like Mission Control. It's not really very DevOpsy. You also need to be able to actually get the file off the container, which may not be very easy. You may not have an SSHD running in your container. So that's led me to the question of, can you bridge observability to bridge JFR rather to other observability tools? And one more thing for you is that JFR 17 introduces JFR streaming. It has no more recordings, and it has real-time capture of JFR events. And what that means is that we are able to bridge it directly into OpenTelemetry. So this is pre-release code. This hasn't been merged to mainline yet, but this is actual OpenTelemetry contrib code to build a Java agent. Here it is. Look, there's the pre-main. And within the pre-main, we submit to our monitor service, which is just a single thread executor. And we basically allow it to record individual JFR events as they occur. And in the metrics bundle, let's have a look at let's say, I don't know, memory. So here is an example of let me zoom in a bit, allocator event handler. So it takes JFR events for allocation of a new young object buffer, what's called a TLAB. And we register ourselves as an event. So here we go. We build up an attribute for the thread's name. We set up an OpenTelemetry histogram. which we do using this builder pattern here. Set the description, set the unit in kilobytes, bind it, and now we have a histogram object. So this is an OpenTelemetry object of down to double histogram. And then each time we get an event come in, we call recorded event. And then from that, we just record the size of the buffer that came in. So there we go. That is the basics of how we would build this. So then we have some OpenTelemetry configuration code. So we create resources, pull in the variables for an API key and an environment variable, set up this builder pattern, which is the metric exporter, set headers, and then this kicks off and starts the network connection to bring us to to send data up to our endpoint. So this is all we need to do. By setting this up, this can now be deployed into any Java 17 application. Well, Java 14 is actually the version that brought in the recording stream class, but obviously Java 17 is the LTS. So this is the Java Flight Recorder recording stream in the package JDK JFR consumer, and then we're able to use that to receive an endless stream of events, which we get callbacks onto our objects from there. Okay, so if I come back to the presentation, I think I'm basically done. So let me repeat my conclusions from before. I hope I've justified everything that was on this list that I came up with at the start. And with that, I think it's questions. And thank you very much. If you've enjoyed Walk today, I've got 2 books you might like: Optimizing Java from O'Reilly, and the 2nd edition of The Well-Grounded Java Developer, which is currently in preview and should be out before the end of the year. Thank you very much.
Thank you so much, Ben. Yay.
That's really a nice overview of the capabilities and what tools are there. And indeed, like you, a lot of people are saying that OpenTelemetry is the future of instrumentation. Yeah, I had a question, for instance, what do you see are the drawbacks at this moment or challenges, but you kind of addressed that towards the end. I was also wondering what's the current adoption at the moment? So how is this used?
Okay, yeah, so I can totally do that. Currently, I would say that the OpenTelemetry adoption is not as widely adopted within the Java community as it is with some others. Go in particular has got a lot of folks interested in it, and I think Java is a little bit behind, but I think that's going to change quite rapidly. Partly because so many of the vendors are now starting to support OpenTelemetry. When I was still at New Relic, we saw a lot of clamor for people who wanted to send OpenTelemetry data directly into New Relic, and so I think the adoption rate has been a little slow, but I think it will actually be picking up quite a lot in 2022. I think if we look forward to that point, it's going to be, I think, rapidly adopted compared to some of the alternatives. I'm trying to think about how to frame the question. It's a little bit tricky because when you say OpenTelemetry adoption, obviously vendors are only going to see people who send their data to vendors. They're not necessarily going to see any data for people who've rolled their own and stood up their own solutions. And right. What I'm realizing is there's actually a lot more of those people out there than I previously thought. So it's kind of a tricky question to answer. I mean, I think one key metric, of course, will be the health and the speed at which the OpenTelemetry Java project moves. And I think that shows, some pretty healthy, what's the word I'm looking for? Pretty healthy hustle. There's a lot of folks in there making a lot of contributions on a week-by-week basis. But like I said in the talk, there's still plenty of room. If I'm perfectly honest, a lot of the people there are vendors, and it would be a lot of help to actually have people who are end users coming in there and helping and just trying it out and giving us their feedback as well.
Indeed. And then if you're talking about, I don't know, the upcoming period, let's say 1 year, what do you think, how do you see it progressing? What are the, let's say, what's the evolution?
Yeah, that's a great one. So I think metrics will be stabilized, and I think that will be a big step forward, because then at that point, with metrics and traces, it's quite compelling. And I think that's actually, to your point, this will be a lot of what drives the growth in OpenTelemetry. At that point, I think certain people may, if you're not already using Prometheus, well, at that point you have a choice, and you're probably going to go OpenTelemetry, I would think. For people that are already using Prometheus and very happy with it, they may take longer to switch over. I think I see both projects as carrying on with decent sized communities for the foreseeable future. On the logging front, I hope we will get a solution for logging out in 2022. But my question here is how quickly that will be adopted. Of the three pillars, logging is the one that I think will take the longest to build up critical mass in OpenTelemetry. Partly because people have been doing distributed logging for a long time. There are lots and lots of people who have things like Splunk and Loggly and all the other distributed logging protocols. And of course, there's a wealth of open source tooling there. So it's already mature. It's already an ecosystem in which there are a lot of very good players. So I think it will be harder and take a longer time for OpenTelemetry to make headway there.
Yeah, that's yeah. I think you're right. There are also a couple of questions from the audience. One, I think I can show it on the screen. Do you see it? Is agent instrumentation?
Yep.
Yeah.
So, okay, so it affected by the strong internals encapsulation in Java 17. Okay, so for people that don't know, what this means is, in Java 11, well, actually really in Java 9, but I only really talk about LTS releases. So in Java 11, direct access to Java internals is taken away. So if you are calling a package, calling a method on a class in a package in, let's say, Java base, bear in mind that from Java 9 onwards, there is no such thing as a non-modular Java application anymore. All Java applications are modular. All your application code and library code might be sitting in the unnamed module, which if you leave stuff on the class path is what you get, but your application is still modular, and Java base is still there as a module. So the exporting requirements of Java base list all the packages that it exports. If you call a public method in a public class in a package which is not exported by Java base, you cannot call it in Java 11. That's the reason I'm so pedantic about that particular point is lots of people don't seem to understand that. The big change already happened. It already happened in Java 11. If you've moved to Java 11, you've already done most of the encapsulation change. The important part of the encapsulation change is already behind you. Okay. What's still present is the ability to cheat and to access things reflectively. And the classic example of this, of course, is Java unsafe, right? That's the classic one. In Java 11, you can turn off the protection for reflection. By default, it permits access to internal packages which you might have accessed reflectively. And in Java 16, it's switched off. And in Java 17, the convenience flag to switch back on the access is gone. You can still do it manually. You can still manually go and open packages specifically for your accesses, but you have to do it all as individual, and you end up with like an enormous command line if you do that on Java 17. But you can still do it. But it is only reflection, so it's not as big a deal as lots of people think. Of course, for Java unsafe, the unsafe package, JDK unsupported, I think that's what it calls. It does actually open those packages for reflection. So some care has been taken about this change of default. So then basically the question is, when what does agent instrumentation do? So agent instrumentation runs as pre-main, and what can happen is you can have problems related to the fact that you want to instrument something which you're no longer given access to directly, because your application for pre-main is still loaded on the application class loader. Now, what you can do in this case is you can hack the Bootstrap class loader, and that's in fact what we do for OpenTelemetry. If you read the code, we do some stuff to inject inject parts of it into the Bootstrap class loader precisely to get around some of these issues. So there are still ways of doing it, but it's it's got harder with 17. I think is what I'd say.
All right, Ben. Well, thank you very much. Yeah, there's another question about the name of your books, but we will share your session, and people can see it there, or they can just Google it. Because at the moment, yeah, speakers cannot write things in this chat. That's unfortunate, but we'll publish the slides.
It's a feature that
Okay.
you're asking.
Yeah,
So
it's a voted feature.
Exactly.
That,
So thank you so much,
great.
and we're looking forward to having you back at Codecamp.